In this video, I'm going to review the questions from test number 2. Okay, so number 1, suppose the electric flux through a region of space is 0. Which one of the following must be true? Okay, so the only time we really talked about electric flux was in relation to Gauss's law. And Gauss's law says that the electric flux through a region is proportional to the net charge inside the region. So if the electric flux is 0, then the net charge inside the region must be 0. Okay. Number 2 is a true or false. The gravitational force between two electrons is typically several orders of magnitude stronger than the electrostatic force between them. This is definitely false. Gravity is pretty much negligible when compared with the electrostatic force. The electrostatic force is many, many orders of magnitude bigger. Okay, number 3. There can be an attractive electrostatic force between a charged object and a neutral object, like a charged balloon sticking to a wall, to a neutral wall. Give the name of this phenomenon and briefly explain how it works. So the name of this phenomenon is polarization, and the idea is that even though the neutral object, like the wall, is neutral, the atoms, the molecules within it, they all have electrons orbiting the nucleus, and the electrons are not free to move around. This is not a conductor, but if you bring, say, a positive object nearby, those electrons are going to want to be attracted to it. So all the electrons, which normally would just be on random sides of the nucleus, they're all going to go over to the one side, right? So, and because all the electrons now are on one side, that creates a net negative charge sort of on the surface, positive charge on the other side, and therefore there will be an attractive force between the two. And that's called polarization. Number 4 was about units. So potential is in volts. It's always measured in volts, V. Current is measured in amperes, A. And resistance is measured in ohms, the omega symbol. Okay, we then had a series of 3 questions, 5, 6, and 7, which compared 2 points A and B. In number 5, A and B are 2 identical charged particles, and suppose that A is 5 times as far from a charged sphere as B. So the picture might look something like this, and if the sphere is charged and B and A are both charged particles, then there's going to be an electrostatic force, and Coulomb's law is going to describe that. And Coulomb's law distance enters Coulomb's law in the denominator, and it's squared, so r squared. So if A is 5 times as far, it would have 5 times as big an r being entered in, and that gets squared, so that's 25 in the denominator. So A would have 1/25 the force of B. A would have a lesser force, B would be stronger, and A would be 1/25 the force, or you could say B is 25 times the force that A feels. In number 6, we have a dipole, and 2 points, A 5 times as far. So the picture would be something like that. And in this case, if you're far enough away from the dipole, we learned that the electric field and hence the force, stuff on top, but it doesn't really matter. R cubed was on the bottom. The electric dipole was weaker, and when it was inversely proportional to R cubed. So if A is 5 times as far, a 5 down here in the denominator along with the R will get cubed. That's 125. So A will be 1/125th the force as B feels. Or you could say B has 125 times the force. It feels 125 times the force. And then finally, in this little sequence of questions, number 7, we have a very large sheet. And again, A and B are situated in the same way. And in this case, we have to remember that a very, very large sheet, I've drawn it, drawn a little rectangle here, but imagine it being much, much bigger, creates a uniform electric field, and hence points, no matter how far away they are, will feel the same force. So they feel the same force, equal force. That's the answer here. In this problem, number 8, we had a sketch of a potential field, so the lines are representing equipotentials. These numbers would be in volts, right? And we're concentrating on this point, and we're told that a positive charge is placed at that location, and we want to know which way the force will go. So positive charges act the quote-unquote normal way. We don't have to flip anything after we figure it out. And a positive charge will go downhill. It will go towards smaller potential, because we think of potential as altitude, right? In the analogy with gravity. And so it'll go down and to the right. It'll roll downhill, so to speak. Similar question. This time we have an electric field, and you see looks to be a uniform electric field pointing downward. And this time we're going to place a negative charge at this dot, and we want to know which way the force goes. Now, positive charges go with the electric field, so a positive charge would go downward, but because we have a negative charge, it's reversed, and so it would go upward. It would feel a force upward, I should say. It would accelerate upward. Number 10, suppose you have a length of ohmic metal, and you apply a certain potential difference to its ends and measure the current that runs through it. Then if you increase the potential difference by a factor of 3, does the current increase, decrease, or stay constant? And if it changes, by what factor? Okay, so we're told that it's an ohmic metal. What that means is that its resistance is constant, and we can use Ohm's law, delta V equals IR, and R will be constant, so that's not changing on us. And so if we multiply the potential difference by a factor of 3 to make the two sides of this equation balance, we would have to multiply the current by a factor of 3. So the current will increase by a factor of 3. I will stop this video here, and the rest of the test will be in a second video.